Well, it's 8:30. I guess if anyone else is going to show up, I guess they can. Pass that around. We got up to gravity last time. We're going to start looking at Newton's law of universal gravitation. We've talked about Newton and what he did before. Let's start off this morning taking a little bit closer look. We're not going to go into great detail of how he developed his theories and stuff, but let's look at a little bit at what he did, the thought processes he went through. Because it really was revolutionary. If you'll recall, at the time, there were the scientific consensus, if you will, was that there were two separate realms of motion. There was the celestial realm and the terrestrial realm. And about 50 years or so before Isaac Newton, thank you, there was another fellow named Kepler. And he did a whole lot of work studying the motions of stars and planets relative to the sun. And, you know, he did all of his work based on the heliocentric model of the solar system, of the universe, actually. Believing that our sun was the center of the universe. Anyway, he worked out some laws of planetary motion, of how the planets move relative to the sun. Not based on any mathematical theory or model of how, to try and explain the physics of it, just by empirically observing the planets and how they moved and making careful measurements of them, where they were, when they were there. And strictly by analyzing the data, he came up with some pretty impressive set of laws that describe planetary motion. Well, they describe it very well, at least to first order. And those were heavily influenced Newton and his thoughts on how all of this stuff worked. Well, we're all familiar with the story of the apple falling out of the tree and hitting Newton on the head. Well, what Newton wondered when he saw that apple fall from the tree and land on his head, he thought, well, according to my laws of motion, in order for the apple to accelerate to the ground, there has to be a force acting upon that apple. And he called that force gravity. Believe it or not, at that point, there was no consensus about this notion of gravity, and certainly not universal gravity. In fact, the whole idea of force acting at a distance without physical contact just seemed counterintuitive to everybody. They didn't like the idea of, what do you mean this magical force that just acts without touching it? It exerts a force on stuff without any contact? How can that happen? They didn't like it at all. Newton wasn't really that bothered by it. He just said, well, it's a force that acts at a distance. And he started, and I think I went through and explained the other day about how he went through that thought exercise of throwing a ball off of the highest mountain peak and how it would follow that parabolic trajectory back to the ground toward the center of the earth. And he realized that if he could throw it fast enough, it would just continually fall towards the center of the earth. But it would, as long as it was moving fast enough horizontally, tangentially to its motion, it would never reach the earth. It would just keep falling all the way around the earth over and over again. Well, he then thought, then maybe it's this same force, this universal attraction between the earth and the moon that keeps the moon circling around the earth. Okay? Because thanks to Kepler, he had some pretty good notions about how planets moved around the sun and things, and he thought, well, obviously the moon is circling around the earth. Maybe it's this same force that it exerts a force on this apple at the tree here above its surface. Why wouldn't it exert a force on this big giant moon that's circling around the same earth? There were other aspects and other things that were also involved here. He got to thinking about the way the planets moved around the sun. And he thought, you know, if that same force that pulls on the apple towards the earth and it pulls the moon towards the earth, then maybe it's that same force that pulls the earth towards the sun and all the other planets towards the sun and keeps them circling around the sun. Well, he started analyzing this, and he noticed that the moon was about 60 times the radius of the earth away. And so it looked to him like then this strange force that we don't have a name for yet, or I don't know if he had a name for it by then or not, but he said whatever this strange force is, it apparently it is proportional 1 over the radius between the two objects squared. And when he analyzed he analyzed the motion of the moon and realized that in order for this force to keep the moon in a circular orbit, it had to be about 1/3600th the force of the same force that acts on that apple or whatever, or a ball or a rock or whatever it is that's on the surface of the earth. And the radius of the earth was more or less known at that time, and that's where he came up with this R inverse R squared proportionality. When he realized that the same force acting on the moon is going to have to be about 1/3600th, about the same force that acts on this apple. And so he said, well, the moon is about 60 Earth radiuses away. If it's 60 times the radius of the Earth away from the center of the Earth, then that's 3,600 is 60 squared. So, okay, well, then it's the radius squared, the distance between the center of mass of both objects. And he got to thinking, because he had, his other laws of motion, his third law of motion, that for every action, there's an equal and opposite reaction. And he thought, well, that means if the mass of the Earth is exerting a force on the moon, then the moon must also be exerting the same force on the Earth by his third law of motion. And he concluded that that means that whatever this force is, it has to be proportional to both masses involved. And that it has to be directly proportional. Well, at that point, it was just a matter of doing a little bit of arithmetic. And he came up with a constant that he multiplies all of this by to make it equal, make it into an equation. And he called that constant G. Now, this is important. When you see the uppercase G with regard to gravity, that is that is Newton's universal gravitational constant. It is not the same as little g, which is the standard notation for the acceleration of gravity on the surface of the Earth, or 9.8 meters per second squared. Not the same thing. This is Newton's universal gravitational constant. And he came up with his law that between any two objects, anywhere in the universe, there is a force of attraction between them that is proportional to the product of their masses divided by the distance between their centers of masses squared times this universal gravitational constant, which I think it's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared? Yeah, per kilogram squared. And with that constant, and knowing the distance between any two objects, he could calculate the force of gravity exerted between them. Of course, like I said, it wasn't really widely accepted at first because people just didn't like the idea of a force acting at a distance. It was something that was just too bizarre for them. It was too beyond their experience, their perspective, their perception. But it worked. And it worked perfectly. It worked beautifully. It precisely described all of the motion, not just terrestrial motion, but celestial motion. It combined all motions. And in fact, that, what I call Newton's unification of the laws of motion, is also called Newton's synthesis. In other words, he took two separate things, combined them, and made them into one. Newton would, in fact, cite Kepler's laws in defense of his universal gravitation. And one of the things he did was he showed that, yeah, Kepler's laws, which were by then established and accepted, because they'd been, Kepler had done them like 50 years before Newton. They were established, they were accepted, they were... and anyway, Newton used them to show that they could be derived mathematically from his universal law of gravitation. And that went a long way to establishing his new law and getting it eventually accepted. Now, I want to point something out to y'all. This force is between any two objects. What I want to show you is that this number here, 9.8 meters per second squared, is actually equal to g times the mass of the Earth divided by the radius of the Earth squared. That's where we get this 9.8 meters per second squared. That's the acceleration due to gravity at the Earth. All you have to do is look at this, to consider that this mass 1 is an object on Earth. It's you or this table or this chair. Well, then we know that the force that is exerted on it by the Earth's gravitational pull is mass 1 times g. Well, that then is equal to mass 1 times the mass of the Earth divided by the radius of the Earth squared. You divide both sides by the mass of the object, you're left with little g being equal to this. Big G times the mass of the Earth divided by the radius of the Earth squared. Because at the surface of the Earth, you are one radius of the Earth away from the center of mass of the Earth, from the center of the Earth. Okay. Now, if you want to start asking what is G as you go deeper and deeper into the Earth, then it starts getting complicated. Did you sign in? Where's the sign-in sheet? You got it? And I just lost my place. Think about this. Think this through. Let's do a little thought experiment. How much would you weigh if you went all the way to the center of the Earth? If you were 0 meters, and we'll ignore the whole problem of the liquid mantle and all of the intense heat and pressure down there. We'll ignore that. Let's just assume that the Earth is just a big ball of dirt, and it's the same temperature all the way through. How much would you weigh if you dug a hole all the way to the center, where R went to 0? You go just by this, then you would think, oh, well, if R is 0, then you would approach infinite weight. That's not what happens. Think about this. When you get to the center of the Earth, you're right here, every piece, every little tiny chunk of mass in that whole ball around you is exerting a force on you of gravitational attraction. That means this little piece is pulling you this way. And this little piece is pulling you this way. And this whole shaft, this whole column of material right here is exerting a gravitational attraction on you in that direction. But at the same time, every little piece of mass in this other column going out in the opposite direction is also exerting an equal and opposite force of attraction on you. So this force vector of gravity will cancel out this force vector of gravity, and the two will have a net attraction of a net force of 0 exerted on you. And of course, that's true all the way around. So when you get to the very center of the Earth, you're weightless. Your weight drops to 0. And in fact, the farther into the Earth you get, the more the outer layers start canceling out each other, and your weight then drops as you get to the middle until it drops to, your weight actually drops to 0 at the center. Because, in fact, this radius r does not go to 0. It becomes distributed to all of these other r's in all equal and opposite directions. And it just completely cancels itself out. That means if you did dig a hole all the way through to China, like you were wont to when you were a child, and you fell into it, you would never come out. You would fall towards the center, but then your velocity would only just barely take you to the other side before you would stop moving out and you would start falling back. You'd end up, because of losses due to air resistance, you wouldn't quite make it all the way here. You would keep oscillating back and forth between the two. No different than if you were drifting away from your rocket ship out in space somewhere and no way to get back to it. I suppose if the hole's rough enough on the side, you might be able to grab hold and maybe climb your way out. But the point is that when you get down to the radius, when you start going into the mass, inside the interior of the mass that's doing the attracting, all of this starts to get very, very complicated to do the math. But as long as you are at some radius equal to or greater than the radius of the body that's doing the attracting, then you can treat the entire mass of the whole body as an equivalent mass at the center of mass, which is the whole point. You can, at that point, it doesn't matter if you're dealing with a giant ball of mass, ME, or if you're dealing with an infinitesimally tiny chunk of matter at the center of mass with that same amount of mass. You're still having that much mass acting on you at that distance. So that's just an interesting little tidbit for you to remember and know that you got to know how you can apply these equations and what they're actually describing. I don't think you're going to run into any questions about the force of gravity inside the planet in the homework or on the exams. So. Still, it's an interesting thing. I mean, it's one of the things that when you start to think about it, it's kind of counterintuitive until you really think it through, and then it's just kind of cool. All right. Let me work out an example here. Because, well, the whole ramification of Newton's universal law of gravitation is that every particle of mass exerts a gravitational attraction on every other particle of mass. That means the two of you sitting next to each other, are actually exerting gravitational forces of attraction between you. There's a gravitational attraction between you and the table and the chair and the floor. And the example here in the book, 5'9", yeah, I know, that would be a whole lot more fun to contemplate if you were sitting next to a hot babe. I get it. But we're not talking about, this is not a biology class, this is physics. All right, the example we're looking at is 5'9". It's on page 120. And it talks about a 50 kilogram and a 50 and a 60? 50 and 70. 50 kilogram hot babe next to a 70 kilogram hunk. Or, whatever vernacular is in common usage amongst people your age today. I don't know or care. But and they're sitting a half a meter apart on a park bench. So I guess maybe one of them doesn't think the other one is so hot after all. All right. What is the actual gravitational attraction between them? Well, the radius is squared, and then that mass 1 times mass 2 just needs to be multiplied by big G. And that works out to, somebody with a calculator do the math, I think it works out to about 9 times 10 to the minus 7. Newtons. Is that what y'all get? I didn't realize this was such a complicated calculation. I guess this is the price you pay for the fancy schmancy programmable calculators. In order to do a calculation, you have to write a program. What'd you get? Times 10 to the minus 7. So, or basically, I think the book puts it at 1 times 10 to, approximately 1 times 10 to the minus 6. Which is, okay, yeah, sure. Point is, if you do that, if you calculate the actual amount of force that is, it's like 1/100,000th of a pound. It's like this. It is literally an immeasurably infinitesimal force. Okay. But it's still there. One of the things that actually helped this whole law of universal gravitation get accepted was that for all of their elegance and beauty and precision, Kepler's laws weren't quite exactly right. There were times when they didn't quite hold true, when there were discrepancies between what his laws predicted should happen and what actually happened. And there was no one could explain why until people started thinking in terms of Newton's universal gravitational law, and then realizing that, wait a minute, the force of the sun attracting those planets and keeping them in under centripetal acceleration, keeping them in orbit, is not the only force acting on them. In fact, every planet exerts a gravitational force on every other planet. Every moon exerts gravitational force on every other planet and on every other moon. And then when they started taking this into account and redoing the calculations of the planetary motion based on Newton's universal gravitation, and they started throwing in all of these little tiny perturbations that this predicted would happen, all of a sudden their descriptions started becoming far, far, far more precise of not only what Kepler's laws predicted, but what they actually observed happen as well. That was a huge step in getting the scientific community to start accepting Newton's theory of universal gravitation as Newton's law of universal gravitation. And this is important. Don't ever forget this. This is the fundamental tenet of the scientific method. That the ultimate test of any hypothesis is the ability of that hypothesis to predict future events. Okay? In other words, if you can't measure it, it ain't science. If it's consensus, it ain't science until it is empirically and experimentally proven, confirmed. All you got is theory, hypothesis. Right? Well, Newton had to deal with that, just like everybody else. Because what he proposed was so beyond the pale of what they could imagine, it took some convincing for people to accept. But, as is usually the case, when something holds out and actually does predict and prove itself to be true and can be experimentally confirmed, people began to accept it. Talked about this apparent weightlessness we talked about weightlessness as you fall through the earth. That was actual weightlessness. You get to the center of the earth and you actually have real weightlessness. You have no weight because gravity is pulling on you equally and opposite in all directions, completely canceling out gravity totally. So you have no net acceleration. When astronauts are in the space station or in the old shuttle, when they still flew those, you could always see pictures of them flying along in the space station or the shuttle with the blob of water floating in the air, and they drop the pencil and it doesn't go anywhere. And they were in apparent weightlessness, but they weren't really. In fact, as we saw earlier, looking at Newton's first thought experiment about throwing a ball around the Earth, anything that is orbiting the Earth or anything else, as long as it's experiencing, its motion is going in a circle, its direction is constantly changing, it is constantly experiencing a net acceleration, a net force. Okay, so the weightlessness astronauts experience in the space shuttle isn't weightlessness at all. What they're experiencing is free fall. They are falling towards the Earth in free fall, but they're also moving tangentially fast enough so that their falling just results in them moving in a circle. Inside the reference frame of their spaceship, they appear to be weightless. But that is an illusion. They are not. They are experiencing the force of acceleration due to gravity the whole time. They're just not moving relative to their surroundings. It would be the same thing if you were in an elevator, someone disabled the emergency brakes and cut the cable. You would, for a few seconds at least, you would feel or experience, you would perceive weightlessness as you fell at the same rate as your environment. Of course, you would abruptly find out that you were wrong as soon as you got to the bottom. And for a split millisecond, you would realize, oh, crud. Let's look at some examples. There's a good example right here. Geosynchronous orbit. How many of you have heard that term? Any of you? All right, have any of you, are none of you familiar with geosynchronous orbit? How many of you watch satellite TV? DirecTV, Dish Network? You've heard of it, right? Yeah. Some of you even had seen it. You notice that those little dishes that they stick on your roof or the outside wall or up on a pole, they're not motorized. They don't have to track the satellite. They just mount them and point them at a fixed position in the sky. And the satellite is always in that exact spot. So once you line it up to the satellite, that's it. You bolt it down and it doesn't move. That's because those satellites are in geosynchronous orbit. They are put in orbit in a position with a velocity so that their position relative to the Earth never changes. They are orbiting at exactly the same rate that the Earth is rotating on its axis. So they're still moving quite rapidly, tangentially, and they're still falling uniformly the whole time, orbiting the Earth, but they're doing so at the same rate that the Earth rotates, so it appears from the Earth's perspective that they are fixed in the sky. They're in a fixed position. So, how fast would they have to go? And at what distance? At what radius from the Earth? What distance above the Earth would they have to be? What would you have to go to achieve geosynchronous orbit? Well, because the orbit of the satellite is circular, it's always in that same position relative to the Earth, so it's moving in a big circle. We know that the force that it's experiencing is centripetal, or it's its mass times its tangential velocity squared divided by its radius. And we know that that has to equal Newton's universal gravitation law. Force. We know that these two forces have to be equal. Well, start by canceling out the mass of the satellite. It doesn't matter how much it weighs. We can multiply both sides by r. Oh, can we? Is it the same radius? Yeah, we can. Just jerking you. Yeah, we can cancel. It's the same radius. Oh. Now, at that point, we have two unknowns. We have a radius and a velocity. Now, I guess we can go ahead and do this. Okay, but we have two unknowns. So, how do we resolve this? What's the key thing about this? We're looking for a special orbit where the velocity of the satellite will carry it one complete revolution every 24 hours. Actually, I think it's, 24 hours is good enough. All right, so we know that the period of rotation of this satellite is equal to 24 hours times 3,600 seconds per hour. And that's what, 86,400? 86,400 seconds. So its period, the time it takes it to rotate, to go one trip, one full revolution around is 86,400 seconds. But what distance will that be at? What is the distance that it has to travel in that 24-hour period? Well, the distance that it has to travel is not pi r squared, that's the area of the circle. 2 pi times the radius. So that is the circumference of the path of the circle that it's going to follow, or the total distance it has to travel in 86,400 seconds. So distance divided by time is its velocity. So we've got 86,400, and I'm doing it backwards. Its velocity is 2 pi r divided by 86,400 seconds. Or, yeah, good enough. So we can rewrite this as 2 pi r divided by 86,400 seconds is equal to the square root of g times me over r, which right there tells you that we shouldn't have taken that square root quite so soon. So let's back up and undo that. And that gives us all of this squared is equal to that. So 86,400 squared divided by 4 pi squared is equal to r squared. Now you can take the square root, and r hold on. Yeah, I've still got an r in there I need to take care of, don't I? So I multiply both sides by an r again, and I end up with r cubed is equal to g times the mass of the Earth times 86,400 squared divided by 4 pi squared. These are all numbers that you can plug in and then take the cube root. Let's see, they give us the mass of the Earth in here somewhere. 5.98 times 10 to the 24 kilograms. And we know that G is 6.67 times 10 to the minus 11. Somebody with a calculator do this? You should get 4.22 times 10 to the 7 meters. Which if you convert it to kilometers, that would be 42,200, 42,200 kilometers from the center of the Earth, not from the surface of the Earth. And it's actually about, according to the book here, it's actually about 3,600 kilometers from the Earth. I'm sorry, 36,000 kilometers above the Earth's surface. You can also solve for V once you've solved for R and find out that V is about 3,070 meters per second. But I forget, I think it works out to somewhere between 20 and 25,000 miles above the Earth if you're doing it in miles. But it turns out that there is that one and only one orbit that will give you actual, true geosynchronous orbit, a true geosynchronous orbit. And it's finite. There's only so much distance around. That means I don't want to call it real estate, but it basically is. The space in that geosynchronous orbit is extremely valuable. Extremely valuable. Because it's finite. You can only put up so many geosynchronous orbits, and then you're out of room. You got no more place to put them. You can't put the next layer out a little further because then it won't be geosynchronous anymore. If it stays in orbit, it'll be moving one way or the other a little bit. If you put another layer a little closer in, try to stagger them, it won't work because you move it just a little closer in and it starts drifting in the sky. They have to be at that exact radius, and that means that there is a finite amount of space to put them. And that's one of the reasons that, they spend a lot of money for the space to put them. Of course, when you spend $500 million building a satellite, I guess the cost of the orbital space to park it is kind of in the, like the guy said when he asked how much it costs to fill up the jet with aviation fuel. The guy said, If you can afford the jet, the cost of the fuel is a little tiny alligator. You just step over those. Everybody see how that was worked out? A couple of things happened as a result of this. You know that because of Newton's gravitational law, it was because of his universal gravitational law that people were finally able to calculate the mass of the Earth. Turned out it was pretty accurate. Oh yeah, here it is. It's example 514 where they determined the mass of the sun based on Newton's gravitational laws. How many of you are familiar with the terms synodic and sidereal? Yeah? No? Synodic and sidereal are the two different terms for two different periods of the moon's orbit around the Earth, based on whether you're observing the moon from the Earth, or they say from the sun, but it isn't really from the sun, because from the sun it wouldn't work out. But if you're observing it from outside the whole system, you can look at it up here. It's on page 128 and 129, or 128, section 5.9. It talks about the moon rising an hour later each day. Right above it in figure 531, it talks about the difference between sidereal and synodic. Basically, if you're standing on the fixed position on the Earth, then you see the full moon every synodic period. But if you're standing out in orbit, not in orbit, but out in outer space away from the solar system, and you watch the moon orbiting the Earth as it all orbits the sun, then you would find out that, well, it actually only takes the shorter of the two for it to complete a full revolution, a full orbit. Because you're on the Earth and the Earth is moving while it's orbiting, it actually appears to take a longer time for it to finish orbiting all the way around. It's an interesting tidbit. You might want to look it up. Don't look for it on any exams. Okay, don't waste space on your index card for the definitions of synodic and sidereal. Any questions? Anybody have questions from the homework? No? All right, well, then I will see y'all on Wednesday.